Swayam Prabha. Digital India. Educated India.
Welcome back to Nuclear Magnetic Resonance Spectroscopy. We are going to look at some of the aspects of NMR, or Nuclear Magnetic Resonance Spectroscopy, that will help us identify a molecule from a spectra. How do we pinpoint the exact molecular structure of an isomer using the isotopes proton or C13? Let's look at this in a little bit more detail. Now, all of the protons in a molecule are surrounded by electrons. Electrons are also negatively charged particles that are spinning. Just like protons are positively charged species that are spinning, electrons are negatively charged particles that are spinning. So if you take an electron, electrons are tiny little magnets by themselves. They have a negative charge and they have a spin. So they create a field around them called the diamagnetic field. So if you have a proton and your proton is surrounded by electrons, the electrons create a diamagnetic field around the protons. Electrons are negatively charged, and the diamagnetic field that they create will be in the opposite direction of the operating magnetic field. So let's write this down. So electron environment will determine the chemical shift of a hydrogen. Electrons are negatively charged particles or energy points that have a spin. They create a very small diamagnetic field around the proton, and electrons create a very small diamagnetic field around protons. The diamagnetic field is going to shield the proton from the spectrometer operating field. Let's say you put in a proton in the spectrometer, and this is just a model, and the proton is surrounded by many layers of electrons. That is going to shield the proton from the magnetic field generated inside of the NMR machine. Now, if you have a thinner electron cloud like this, that is the shielding that you have from the magnet would be less. So therefore, it means that if you have more electrons around a proton, you will be more shielded. That means the magnetic field that you feel in the presence of these huge layers or big layers of electron would be less. If your magnetic field is less, then your frequency would also be less. So in essence, B effective is the magnetic field that's experienced by the proton inside of an electron cloud, because all protons that we are going to look at are in a bonding relationship with some other atom, mainly carbon, sometimes oxygen, sometimes nitrogen. So they have an electron cloud around it. In the bonding electrons are around the hydrogens. The effective magnetic field here is equal to the BO of the machine, or operating magnetic field of the machine, minus the B local, or this is the one created by the electron, the diamagnetic field around the nucleus. So if you have a lot of electrons around a proton, then your B local would be high. If your B local is high and BO is a constant, which is the machine's magnetic field, which is really very high, and these are tiny amounts, even then this is going to be a little lower. So let's say we have a proton with a lot of electrons around it. So let's say it's connected to some atom that's electron donating, and so you have a lot of electron density around it, which means your diamagnetic field is going to be a little higher. Therefore, it's going to take away from the field that's exerted by the magnets. Therefore, the B effective is going to get lowered. The higher the B local, the lower the actual field that's felt by the proton. In other words, these protons are being shielded by these electrons. All right, let's write that down. So proton is in a shielded environment, shielded by electrons. That would mean B local is high. Therefore, B effective is low or lower. So for shielded protons, the B effective is lower. So you're really shifting to a smaller effective magnetic field. Therefore, your frequency is also going to be lowered in this direction. Therefore, the chemical shift is also going to be lower from TMS. Okay? So chemical shift is lower. So we are comparing everything with TMS as we talked about in our previous video. Let's say you have a proton and it's connected to an electron withdrawing group. So which means it's going to pull all those electrons away from the proton. Now the local field or diamagnetic field created by those electrons would be lower. So if you take this equation, and I'll write that again, B effective is BO minus B local. The diamagnetic field is going to be lowered. But the machine magnetic field is a constant. That's set by the strength of the magnet. That's a constant. Therefore, the B effective is going to be higher. So what this means is protons in a D-shielded, so if this is shielded, that means it's got a shield of electrons around it. The electrons are shielding it from the magnetic field. Here, you are pulling those electrons out and you're de-shielding it. So when the proton is in a de-shielded environment, that means the electron density around the proton is thinning out or less. The diamagnetic field created by those electrons would also be low. So that means B local would be lower. If B local is lower, this is a constant, therefore this is going to be higher. We are comparing everything to TMS. So B effective is higher. That means you are having a higher B effective is going to be higher. So this is going to be B effective. When B effective is higher, then your frequency between the alpha and the beta states will also be higher by very small amounts. But that is enough to give you a signal that is going to be shifted away from TMS. We have set TMS to 0. So this is going to be a shift. So chemical shift is going to be higher. So delta will be higher. So in essence, what we are trying to say is that if your protons are in an environment with lots of electrons around it, it's going to be shielded from the magnetic field of the machine. And therefore, it takes less energy to flip the spins from alpha to beta state. So when you have less energy to change the spin from alpha to beta, your frequency is also going to be lowered because E is equal to h nu. Lower the energy, lower the frequency. If your frequency is lower, then your delta is also going to be lower, because the delta, or the chemical shift, is basically frequency shift from TMS over the machine frequency, which is a constant. So therefore, when you have a B effective that is higher, your frequency will be higher, and therefore your chemical shift will be higher. So that's pretty much what we are seeing in this chart here. Look at all the hydrogens and their delta values, or their chemical shift from TMS. TMS is set to 0. So TMS is tetramethyl silicon. Silicon is electropositive compared to carbon. Therefore, it doesn't grab any electrons from carbon. All of those electrons are around the hydrogen. It's very shielded. So you can think of this as TMS. Now, if you put electron withdrawing groups, they're going to pull electrons away from it. If you have methane, it's going to be the delta is going to be 0.21. If you put an iodine, the chemical shift is going to be 2.68, and so on. Bromine 3.04, chlorine 3.4, and fluorine very high, 4.26. Now we all have seen Pauling's electronegativity table, and you can see that the electronegativity values here are in proportion to the delta values, which means the more electronegative the group that is connected to the carbon bearing the hydrogen, the more de-shielded your proton would be. And that's what you see, a higher number. When you go down here and your electronegativity drops, you can see that the de-shielding here is going to be less, and the shielding is going to be more. And that's what you're seeing here. Your delta is the chemical shift from TMS. TMS is 0. This is shifting from TMS. So the frequency shift from TMS is lower when you have shielded protons. So here is a chart that tells us the chemical shift for hydrogens in different environments. As you can see, primary is the one that is most shielded, primary alkyl, so like an RCH3. That's the most shielded, and it'll have a very low value, less than 1 ppm. Secondary is going to be right next to it, RCH2R. It's about 1.2 to 1.4. Now, tertiary is a little bit more de-shielded, RCHR2. That's going to be about 1.4 to 1.7. So you can have a Lily carbons, that means you're next to a double bond, and for these hydrogens, even though it could be a primary, the fact that you're next to a double bond, it's going to be more de-shielded. If you're next to a ketone, let's say a hydrogen that is over here, that's about 2.1 to 2.6 about. If you're next to a benzene, that's not on the benzene, but you're next to it, so that's a benzylic proton, that's about 2.2 to 2.5. Okay, so these regions here will tell us to some extent what the functional groups are. So if you see a proton around 2, then you could look for carbonyls or phenyl groups right next to it. If you're on a triple bond, that is about 2.5 to 3.1. You're not really very de-shielded, okay, compared to vinylic protons. Now, after this, all of the ones that are next to electron withdrawing groups, so let's say you have an electron withdrawing group here, let's say a halogen, those are going to be somewhere in the range 3.1 to 3.8, where X is going to be either iodine, bromine, or chlorine. Now, if you are on the double bond protons here are much more d-shielded than the alkyl protons. So these vinylic protons are going to be about 4.6 to 5.0. Now, sometimes vinylic protons can also be more d-shielded than that. Let's say you have a hydrogen here. You can go up to like 6, 5.2 to 6. Okay. Now, if you have them on benzene, they are going to be very d-shielded. So these are kind of a class of their own. If you have benzenes, you got to check in the 7 region, 6.0 to 9.5. Typically 7.2 for regular benzenes. Why is that? Why is there such a huge leap between, let's say, a hydrogen on the benzene versus a hydrogen next to a benzene? If you take a benzene here, the benzene has got an aromatic ring. So the aromatic ring has electrons circulating on top and bottom because of the resonance. So benzene has got resonance. When we draw benzene resonance, we put these pi bonds in a ring here and circulate them. So basically they are running around the ring constantly. And so if you draw an actual benzene, you have a ring of electrons going around the benzene. Okay? And sometimes we draw benzene like that. We draw it with a ring like that. That ring is an electron ring. Electrons, as we said before, are negatively charged particles. They have a spin. And in a magnetic field, they create their own magnetic field. It's called a diamagnetic field. And this diamagnetic field that the benzene creates is going to be in the direction of the applied magnetic field. So when the applied magnetic field and the ring current created by circulating pi electrons are in the same direction, then the B effective is high. So these hydrogens are experiencing a much higher magnetic field. When the magnetic field is higher, then you know the frequency is also going to be higher, which is the reason why you have such a high number for these hydrogens, mainly because of the electron ring current. Something similar can happen even with pi bonds, okay, which is why you have a small ring current here and these are d-shielded. Now, when you have a carbonyl, it's even higher than that. And so these hydrogens can be very d-shielded. And they are going to be about 9 to 11. So 9.5 to 10.5. The highest of all of them would be carboxylic acids, these protons. They are sometimes close to 12, so about 10 to 13. They are the most d-shielded. The scale is from 0 to 10. So these, if they are more than 10, they will put a small box inside the spectra and say inset. And if it's say, let's say it's at 12, then they will say inset at 2 ppm. So then you add that to the regular ppm on the X scale. Add that to 10. Okay. So this is a very important chart, and I hope you know that you would always use this. So just by looking at these numbers, you can to some extent guess what the functional group is. So if you don't have an infrared, this is kind of an invisible tool there that can be used to find out neighboring groups and functional groups. All right, so let's look at the second effect. So we said nuclear NMR spectra has 3 very important effects. One is the chemical shift that tells you the environment of the proton. Spin-spin coupling that tells you all about the neighbors. Integration that tells you how many hydrogens are there per peak or buried underneath each of those peaks. These 3 pieces of information is really sufficient to solve for the exact structure of an isomer. I will talk to you guys soon. Bye.